Hi everyone and welcome back to That's Engineering. So in this second video for the two-way ANOVA, we are going to be looking at the SPSS implementation. In the first video, we covered the design of the two-way ANOVA and the steps that we will follow. And if you guys haven't checked out that video, I'll leave a link to it down in the description below. If you guys like this content, don't forget to leave me a thumbs up, and as always, please subscribe. Right, so a quick recap from our first video. The first step is going to be collecting the data and tabulating it. We will then test for normality and equal variances, and if these two are satisfied, we will then run a statistical test, which is going to be the two-way ANOVA. We will then test for an interaction between our two independent variables, and if there is a significant interaction, we will run a simple main effects analysis. We will then run a post-hoc test, which is going to be a 2-key HSD, and then interpret our results and maybe even tabulate some descriptive statistics. So this is the design of the experiment. We had two independent variables. The first is model with three levels, model 1, 2, and 3. So each model actually represents a neural network that I designed and I was comparing and testing out. And the second independent variable is strategy, again with three levels, and this is sort of like the learning strategy, and I had three learning strategies for each of my three neural networks. The dependent variables are my performance metrics, in this case error and correlation, so I have two dependent variables. Now for a two-way ANOVA, we traditionally have three null hypotheses. The first is that the means in performance metrics across the three models would be the same, or that there would be no significant difference for all dependent variables between the three models. The second null hypothesis is that the mean performance metrics across the three strategies would be the same. And the third null hypothesis is that there will not be a significant interaction between model and strategy, meaning that these two independent variables do not affect the overall mean outcome of the experiment. However, if we reject the third null hypothesis and there is an interaction effect, then we would perform a simple main effects analysis. So in this analysis, what we do is we sort of hold one independent variable constant and then test out the means for the other independent variable. So for example, in the first case, we hold strategy constant, and then for each of the three strategies, we test out the means between the three models. And in the next case, we hold the model constant, and for each of the three models, we test out the means between the three strategies. So with this, let's get down to the SPSS implementation. Alright, so this is our data on SPSS. Let me hop into the variable view. As you can see, I have my two independent variables, model and strategy. They are nominal measures. And my dependent variables, error and correlation, which are scale measures. For each independent variable, I have three levels. It's my three levels of model and my three levels of strategy as well. And you can see that in the data view as well. I have model 1, and under model 1, I have strategy 1, strategy 2, and strategy 3, each with 10 data points. So I have equal sample sizes, and then that continues on model 2, and under model 2, I have the three strategies, and the same for model 3. And for each instance, I have my performance metrics of error and correlation, which are my dependent variables. Now, before we look at any descriptive statistics, let's jump into analyzing the normality of this data set. Is it parametric or non-parametric? Now, traditionally, what we would do is you would go to Analyze, Descriptive Statistics, Explore, and then you'd single out your independent variables and your dependent variables. You choose plots and select normality plots with tests. However, because we have two independent variables, we need to test for normality across all combinations of model and strategy. This is because normality needs to be tested across each independent variable. So for two independent variables, we need to split our file and test for every single possible combination. And to do that, what you need to do is you need to go to Data, and from Data, go down and find Split File. Click that and choose Organize Output by Groups, and put in your independent variables into the list and click OK. And then SPSS will tell you that the split file has been performed. After you do this, then you can run the test for normality. So go to descriptive statistics, explore, If you have your independent variables, put them in here. Your dependent variables, put them in here. At the moment, I'm not interested in any statistics. I just want normality, so I will select plots. Go to plots. I don't want any descriptive statistics. I don't want any other plots. I just want this. Tick this box, normality plots with tests. Click continue and then click OK. And this will generate. Right. So I'm going to bring this up a little bit. Scroll to the top, and very quickly I'll just minimize all of these. So you can see that it's performed the normality test for every combination for model 1 across the 3 strategies, and then for model 2 across the 3 strategies, and so on and so forth for model 3. So when considering the normality of this entire dataset, you need to consider all these possible combinations and evaluate the dataset as a whole. So for example, if I take model 1, strategy 1, and jump to the tests of normality, you can see there are 2 tests. There is the Kolmogorov-Smirnov test and the Shapiro-wilk. We will consider the Shapiro-wilk test. And what you do is you look at the significance of the test. So in the case of Shapiro-wilk, the null hypothesis is that the data set is normally distributed. And the alternate hypothesis, in which you reject the null hypothesis, is that the data set is not normally distributed, or it's non-parametric. And the alpha value we are working with is 0.05. So if the significance or the p-value is less than 0.05, we reject the null hypothesis and say that the data set is non-parametric. So in this case, both my significance values for error and correlation are greater than 0.05. We cannot reject the null hypothesis, so we can conclude that in the case of model 1, strategy 1, both my dependent variables are normally distributed. And you can even look at the Q-plots to grasp that information. And then you can perform this for model 1, strategy 2, model 1, strategy 3, so on and so forth. So just as another example, I'll take model 3, strategy 1. And if I look at the tests of normality, again, I can see both my significance values are greater than 0.05. So I cannot reject the null hypothesis, and I can conclude that this dataset, in the case of model 3, strategy 1, is normally distributed. So what I've done is I have tabulated all the data over here. So again, this is our null hypothesis. And if p is less than 0.05, we reject the null hypothesis. I have model and I have the 3 strategies, and I have the significance or the p-values for every combination which I have tabulated. And you can see that there are a few instances, as highlighted in red, where the data set is non-parametric or not normally distributed. Now, what you can do is you can single out these cases and say, okay, so for these cases, the data is not normally distributed. We cannot run a parametric test. But we're looking at the overall data set. So when you consider the overall data set, majority of the data is normally distributed. There are just a few outliers which are not normal. So you can conclude that the overall data set is parametric, or it's normally distributed, and then you can proceed with the analysis in this sort of a manner. And that's exactly what we're going to do. So as majority of our values are normally distributed, we can conclude that our overall data set is parametric. Now, once that's done, don't forget to hop back into SPSS and remove the split file so that you can continue with the analysis. So I'm just going to select these two, move it back, and remove the cases and do not analyze by groups. Okay, and the split file has been removed. Alright, so the final test before we get down into the two-way ANOVA is to test for equal variances. For that, go to Analyze, General Linear Model, and select Multivariate. Make sure your independent variables are under fixed factors and your dependents are under dependent variables. Then go down to Options and tick Homogeneity Tests. Make sure your alpha is at 0.05. Click Continue and then click OK. Scroll down until you reach this box, Levene's test of equality. And this is how we test for equal variances. So you would get your dependent variables, error and correlation in this case, with a bunch of significance values. But the values we are interested in is based on mean. So in this case, for error, it's 0.004, and for correlation, it's 0.002. So that's what I have here. I've tabulated it. Error and correlation. However, both these values are less than our alpha value. So we reject the null hypothesis and we can conclude that our dataset does not have equal variances. Now, when performing an ANOVA, there are three conditions that have to be satisfied. The data has to be normally distributed. That is satisfied for our dataset. It has to have homogeneity of variances. That is not satisfied. And it has to be independent random samples. And these are independent random samples. However, ANOVA is quite robust to non-equal variances. So even though we cannot confirm that we have equal variances in our dataset, we can still run an ANOVA. But this must be stated as a limitation of your study. So the next step in our analysis is to perform the two-way ANOVA. And you can do this by going to Analyze, General Linear Model, and choosing Multivariate. Again, your independent variables go into fixed factors and the dependent variables go over here. And that's it. You can just click OK and it will run and give you the results of the two-way ANOVA. So what you need to do is scroll down to this tab, Tests of Between Subject Effects, and we're interested in three rows. The first is Model, Strategy, and Model into Strategy. So Model into Strategy is our interaction effect. And for each of these rows, for example, model, you have your dependent variables, error and correlation, and their corresponding p-values, which are shown over here. You have the same for strategy and the same for the interaction effect of model into strategy. So I've taken these p-values and I've tabulated it as such. So what happens in the two-way ANOVA is, first of all, considering model, what we do is we ignore strategy and look at if there are significant differences between the performance metrics for the three models or the three levels of the independent variable model. And in this case, the values are less than 0.05, which is less than our alpha. So we can reject the first null hypothesis and say that the three models significantly vary in their performance metrics. That's error and correlation. Then we move on to strategy. So what we do here is we ignore model and look at if there are significant differences between the three strategies only. And again, the p-values are less than 0.05. So we can reject the second null hypothesis and say that error and correlation significantly vary between the three strategies as well. However, this can be slightly misleading because the way this is performed, it considers one independent variable without the other, meaning it's considering the model without looking at the strategies, and then the strategy without looking at the models. And this may be incorrect because the model is a neural network, the strategy are learning strategies, and so the learning strategies influence how the neural networks operate or would influence how the model operates. So we need to consider both together, and we would expect an interaction between these two independent variables, and that's what pops up in the third null hypothesis. So model into strategy looks at the interaction effect. For error and correlation, both the p-values are less than 0.05. So we can say that there is a significant interaction between the variables of model and strategy. And because of this interaction effect, this two-way ANOVA sort of becomes, I won't say invalid, but it can be misleading. Because the mean effect of one variable, which is model, depends on the levels of the second variable, which is strategy. So because of this, we need to perform something called a simple main effects analysis, which is in essence a variation of the two-way ANOVA. So that's all right. So now we're going to look at the SPSS implementation for the simple main effects analysis. So we performed the two-way ANOVA previously, and we saw that there was a significant interaction effect between our independent variables, which means the effect of one variable, that's model, depends on the levels of the other variable, strategy in our case. And what we want to do is we want to actually test if the three models significantly differ in performance for each of the three strategies. So we hold strategy constant and test across the three models, and then hold model constant and test across the three strategies. So the way in which you would perform a simple main effects analysis is more or less the same. Go to Analyze, General Linear Model, and choose Multivariate. Make sure your independent variables are the fixed factors and your dependent variables are on top over here. In this case, we're going to go ahead and choose a post-hoc test. Choose your factors, add them here. And you can actually choose any post-hoc test depending on your experiment or your study. But I'm going to go with a 2-key HSD, quite traditional. Click continue. Then going to go over to EMMEANS. So click EMMEANS, choose model into strategy, and display means for model into strategy. This is our interaction effect. Again, click continue. Now before you click OK, go ahead and click paste. And this will actually open up a script. So what you have to do is find this particular line, model into strategy, and replace it with 2 lines of code. I'm going to write those 2 lines down in the description so it's easy for you guys to copy and paste it. So those 2 lines of code are over here. I'm just going to copy it again. And I'm going to paste it over here. So in essence, I'm finding the EMMEANS, so model into strategy, that's my interaction effect, and I'm comparing model adjusted to the Bonferroni correction. And then I'm comparing again strategy, again adjusted to the Bonferroni correction. So what the Bonferroni correction actually does is it adjusts the alpha value or the significance depending on the number of strategies and models. And this reduces the type 1 error, thereby minimizing the number of false positives. If you don't want to change the alpha value or maintain the statistical power, you could probably try LSD, a least significant difference. And what you can do is you can actually type it out, LSD, and it will give you the options over here. But I'm still going to use the Bonferroni correction. So once these 2 lines are in place, go ahead and click the run button over here. And these are the results that it will give you. So if you scroll down, you'd actually find the tests of between subject effects, which is our traditional 2-way ANOVA. But what we are interested in the simple main effects analysis is actually the univariate tests. So I'm going to keep scrolling down until I meet my first univariate test. So this is the results for the simple main effects analysis. So I have my dependent variables error, and I have strategy over here. So what's happening is I'm looking at strategy 1, so I'm holding strategy 1 constant, and then looking at if there are any differences in the performance means between model 1, 2, and 3. And for example, in this case, strategy 1 has a significance less than 0.05. So I can say that for strategy 1, there is a significant difference between the performance of the 3 models. If I look at strategy 2, for example, my significance is 0.083. So for strategy 2, I can say that there is no significant difference in error between the 3 models for the second strategy. And I can draw a similar conclusion for strategy 3, and then the strategies again for the dependent variable correlation. So I'm going to tabulate this a little later on, but let's keep scrolling until we meet the second univariate test, and that is right here. So again, my dependent variables, error and correlation. Now, in this case, we are keeping model constant. So we are holding model 1 and looking at if there are any significant differences in performance between the 3 strategies. So in this case, the significance is less than 0.05, a very small number. So what we can say is for the first model, there are significant differences between the error in strategy 1, between strategy 1, 2, and 3. And if we look at this value, for instance, we can say again, P is less than 0.05. So there are significant differences in the 3 strategies for model 1 for correlation, which is our dependent variable. So let's jump back into the Excel sheet. I've actually tabulated everything over here. These are the 2 commands that you need to copy. We have a Bonferroni correction, and this is our simple main effects analysis. So this is our first univariate test. So what it shows us is for strategy 1, there are significant differences in the performance metrics between the 3 models. However, the 3 models did not show any difference for strategy 2 because our p-values are both greater than 0.05. And for strategy 3, there is a significant difference in error between the 3 models, but not in correlation, which means if you consider strategy 3, all 3 models had roughly the same mean correlation, but had different values of different means, significantly different means for error. And this is our second univariate tests. Everything was less than 0.05. So they all had significant differences. And what you can say is for model 1, there were significant differences between the three strategies, as for model 2, as for model 3. And this is the simple main effects analysis. But where these differences lie, that leads us to a post-hoc test. So let's go back to SPSS and scope out our post-hoc test. So I'm going to scroll back up to the top, and we're going to go down again until we meet the pairwise comparisons. And the first one is here, and this is our 2-key HSD post-hoc test. So again, we have our dependent variables, error and correlation. Let's look at error first. So what's happening here is for strategy 1, we are now comparing model 1 versus model 2, then model 1 versus model 3, then model 2 versus model 3, so on and so forth. So, for example, model 1 versus model 2, our significance is 1, which is much greater than the alpha value, and we can say that there is no significant difference between model 1 and model 2 for the first strategy. However, if you look at model 1 and model 3, the significance is much less than 0.05. So we can say that there is a significant difference between model 1 and model 3 considering strategy 1. And you can then draw similar conclusions for all the combinations of the three models for each of the three strategies for error, and then perform the same thing for correlation. So if you remember from our simple main effects analysis, strategy 2 had no significant differences. I will pull that up again over here. Strategy 2 had no significant differences in performance metrics across the three models. And that would be reflected over here in our post-hoc test. You can check strategy 2. And if you look at all these significant values between the three models, you'll see that they're all much greater than 0.05, which means there are no significant differences in models performance for strategy 2, considering both error and correlation. So this is our first pairwise comparison. We're going to keep scrolling until we reach our second pairwise comparisons. And now in this case, we have model and the strategies versus each other. So again, for error, model 1, strategy 1 versus 2, strategy 1 versus 3, so on and so forth. So most of these show significant differences. And for example, we can say for model 1, there's a significant difference when you use learning strategy 1 versus 2, 1 versus 3, and 2 versus 3. And then you can say the same for model 2 and the same for model 3. So I have also tabulated all the post hoc results, and that's what I have over here. So strategy 2, no significant differences. I am not going to tabulate these values. I have no significant differences for correlation from strategy 3. Again, haven't tabulated those values. But the values in green are where there are significant differences. So if you were to draw conclusions from this post hoc test, you could say that model 1 versus 2 over here for the first strategy shows no significant difference, meaning they are more or less the same performance. But model 1 significantly differs from 3, and model 2 significantly differs from 3 for the first strategy. You can then conclude that all three models perform equally well for the second strategy. And for the third strategy, model 2 significantly differs from model 3, but model 1 does not significantly differ from model 2 or 3 with regards to error, and there are no performance differences with regards to correlation. You can then look at the second pairwise comparisons, and this shows us that for model 1, there are differences when you consider the learning strategy 1 versus 2, 1 versus 3, and 2 versus 3 in error for all three, in correlation for just the first two. In my study, when I was doing my research, I didn't really use the second pairwise comparisons as this data was redundant. But you could probably use it depending on the nature of your study or the nature of your experiment, and of course the nature of your independent variables. So in this sort of a manner, you can actually draw appropriate conclusions based on the post hoc test and the simple main effects analysis. However, once you draw these conclusions, you would want to know how far each of these differences take place. So for example, we know that model 1 differs from model 3 given the first strategy because our error and correlation are both less than 0.05. But which one actually performs better? Is it model 1 or is it model 3? We know there's a significant difference, but which one has the better performance and which one has a weaker performance? So to find this out, we go into the descriptive statistics, which we will look at next. Alright, so in the final step, we're going to look at tabulating our descriptive statistics so that we can gauge which model performs better than the rest and which learning strategy performs better than the rest. So before you tabulate your descriptive statistics, don't forget to split file again. And this is so that we can get our descriptives for every level of model and strategy, every combination of model and strategy. So go back to data, split file, choose organize output by groups, select your independent variables, drop them there and click OK. And once that's done, you can go to analyze descriptive statistics. You can choose descriptives over here, or you can go to explore, choose statistics, make sure your factors are here, your independent variables. Your dependent variables up here, click statistics, make sure descriptives is checked and your confidence interval is 95% or whatever percentage you need for your study. Continue and click OK. And these are your descriptive statistics. So for example, in the case of model 1, strategy 1, for error and correlation, these are the mean values, your standard deviations, you're given maximum, minimum, range, IQR, median, variances, and even the confidence interval. And then you'll have for strategy 1, and then model 1, strategy 2, and so on and so forth. So what I've actually done is I've gone ahead and tabulated all the descriptives in this table. Let me very quickly run you guys through it. These were the results for the simple main effects analysis, the first bit. So we know that there is a significant difference between the performance of the three models given strategy 1. Strategy 2 has no significant difference, and with strategy 3, the only difference is with error. And these are the results from the 2-key HSD post-hoc test. Again, we know that for the second strategy, no differences. For third strategy correlation, there are no differences, but differences do lie between model 1 and model 3 for strategy 1, for example, and model 2 and model 3, and then in model 2 and model 3 for the third strategy, and that's shown by this value over here. And finally, I have my descriptive statistics. My data set is parametric, so I have considered mean plus minus the standard deviation. If my data set was non-parametric, I'd be looking at the median and the interquartile range instead. So for model 1, these are the performance, this is the error for strategy 1, 2, and 3, and the overall error and correlations as well. So error on this side, correlation on this side. And I have the same for model 2 and the same for model 3. So if I just revise this a little bit. So for example, in this case, strategy 1, model 2 versus model 3, there is a significant difference. I'm going to find that here. Strategy 1 was 0.32 for model 1. Let me highlight this value. And strategy 1 for model 2 was also 0.32. Sorry, I'm looking at model 2 versus model 3. Okay, sorry, I made a mistake. I'm looking at strategy 1, model 2, which is this, and strategy 1 on model 3, which is this. So I can see that model 2 has a lower error, 0.32 for the first strategy, versus model 3, which has a slightly higher error, 0.37. But this difference in error is significant. So I can conclude that for the first strategy, model 2 performs better. But if I was to compare model 2 strategy 1 versus model 1 strategy 1, I can see that it's the same value. So there is no significant difference. And that's highlighted over here by the fact that model 1 versus model 2 for strategy 1, no significant difference. So let me close that as well. We know that for strategy 2, all the models performed equally well. So this is 0.16, this is also 0.16 in error, and this is 0.18, but no significant difference. The values are quite close to each other. Same for correlation as well. You could also probably check something like this: model 2 versus model 3, strategy 3. So choose a different color. Let's go with blue. So strategy 3, model 2, strategy 3, model 3, and again you can see that model 2 has a lower error than model 3. So just from these two results alone, we can conclude that model 2 performs better for strategy 3 and 1 than model 3, which means model 2 has lower error and is probably the better model regardless of the learning strategy. So you can go back and forth. You can analyze each combination, each variation depending on your study, and you can draw appropriate conclusions and interpret your results as such. So this is just one way of interpreting this system. It's up to you, depending on what your independent variables are, to interpret and draw your own results and your conclusions of your study. Alright everyone, so that's the end of this video. We looked at the two-way ANOVA, its SPSS implementation, and how and when we need to apply a simple main effects analysis. We also looked at interpreting our results and drawing our conclusions based on our data and our post-hoc tests. So like I mentioned previously, this analysis was used quite extensively in one of my studies. I've left a link to my publication in the description down below. If you guys are interested, you can go ahead and read my paper. It's about neural networks, so if you're into AI, that might interest you. If you like this content, don't forget to leave me a thumbs up. Oh, there it is. And as always, please subscribe. I'm Chums. Thank you all for watching, and I'll see everyone in the next video.